In this video, I would like to introduce you to Chapter 4, Heating Load Computations, give you an overview of determining the area of wall or floor or ceiling in which the heat loss occurs. So what we have to do first, we have to look at the building envelope and what we have to do is look at the loss through the building envelope in the winter to the outside conditions. So we're particularly concerned about the location of the building and what the outside design temperature is, because it's the difference between these two temperatures that drive the heat loss and heat gain of the building. The heating load will determine the requirement for the furnace of a building or the heat pump for a building. So we will do this procedure of heat loss for each room of a building, and the total sum of all rooms will become the heat loss for the entire building. The heat loss consists of three sources. The loss through transmission. This is the physical wall. So like if you have a brick veneer or a siding building, it's the loss through that part, which I will refer to as the opaque wall that you cannot see through of the wall or of the ceiling or the floor of this building. So that's one source, is through transmission. The other source is through infiltration of air around cracks of a window. And the third one will be the ventilation, which can be exhaust fans from bathrooms or restrooms or kitchens. Or it can be ventilation just by opening and shutting of doors in normal use of the building. The outside design temperature we have to determine. This is located in your book on page 117. And it shows here that the outside design temperature is 14 degrees in Richmond. The inside design temperature shown here for the winter is 68 degrees. So the difference between 68 degrees minus the 14 degrees is our delta T, or the temperature difference. So this chapter deals with all three losses, the transmission, the infiltration, and the ventilation. But the transmission loss is what I'm going to deal with first. The transmission loss is expressed as a value of Q. That's the heat loss for the building, and the rate of the loss is a lowercase q, or BTUs per hour. And the equation for the transmission loss is Q equals UA delta T. Now earlier I mentioned the delta T being 68 degrees minus 14. The A is the area of the wall or the floor or the ceiling in which the heat flow occurs, and the U is the rate in which the loss occurs. So the U value equals 1 over the total of the resistance values for a wall or floor. So in previous chapters you looked at the resistance of brick, gypsum wallboard, insulation, and you'll sum up all of those and divide it into 1 to get the U factor. Then you'll take that U factor and multiply it times the area of the wall times the temperature difference. So if you look at this example here, I have a room which has a wall of 13 foot and 12 foot. So over to the right, I'm discussing the loss through the west wall. This room has a loss through the west wall and it has a loss through the south wall. So we would have two things we would have two sources of loss through the walls. And then we would have a loss through the floor and a loss through the ceiling potentially. The wall that you see here and here, these two walls do not have any loss because they are conditioned space on the other side of that wall. So to get the transmission loss through the opaque part of the wall, that being the wall in which there's no window, we take 13 foot, which is the length of the wall, times 8 foot to get 104. We then subtract the square footage of the window. The window is a 3 by 5 window. And we just come up with a net of 89 square feet. So to get the Q out of this equation, we'll multiply U times A times T. This is the A. A equals 89 square feet. So really, in trying to reduce heat loss through a building, the U factor is what you can really control by adding additional resistances and therefore reducing the heat loss through the building.